Okay, ladies and gentlemen, welcome to Salzburg. Welcome to the state of Salzburg. Welcome to the city of Salzburg. My name is Arne Wartke, and I have the great privilege to welcome you here. Some people still migrating into the room. And yes, if you hadn't had a chance to register this morning, because there was fortunately a long line, it means a lot of attendance even for the opening session, then please register sometime in one of the coffee breaks. For many of you, this is actually welcome to Austria as well, because you have come from around the world, from the Americas, North, Central, and South, from Europe, Africa, from Asia, and from Australia, from all around the world, from 50 different countries. About 800 participants, some of them are with us online, and many of you obviously here, and I hope you enjoy the stay in Salzburg. We're really honored to host IDW here, a festival of data in the festival city of Salzburg. We're really happy to have you here, and we hope also to keep you here. Now, we compete with Salzburg, and we compete with the weather, but we also have a really exciting and really important program. So as we're competing, we're trying to help you a little bit, because together we will go to the residence. For those of you who have tickets for the musical evening that is sponsored by the state and the city of Salzburg, if you have a ticket for the musical evening, and it is kind of exciting to hear Mozart played at those places where his works were originally performed. If you can't go for some reason, or if you decide you want to hang out with your friends that you haven't seen in a few years, please take your ticket stub and give it to somebody who doesn't have one, because we're fully booked for that event. It's a historic building, and there's a limited capacity. So if you can't go, maybe somebody else can enjoy the magic of this concert. Yeah. So State of Salzburg is actually one of our great supporters, not only in sponsoring this concert, but in many other ways, has supported the development of our new faculty. The College of Digital and Analytical Sciences has supported the university, has supported smart digitization in the state. For example, there's an initiative on digital museums, making the museums more digitally accessible, and has also helped us with our Intelligent Data Analytics Lab Salzburg. And representing the state of Salzburg here is the head of the state of Salzburg, the Landeshauptmann in Austrian. In German, it would be the Ministerpräsident. Let's welcome on stage the governor of the state of Salzburg, Dr. Wilfried Haslauer.
Good morning, everybody. Dear Dean Bartke, dear professors, scientists, ladies and gentlemen, a very warm welcome to Salzburg. It's my great pleasure to open the International Data Week in Salzburg. The Science Congress has come to Europe for the first time, and therefore it's a special honor for Salzburg to host it. We're very pleased with the Faculty of Digital and Analytical Sciences at the University of Salzburg. Thank you, Professor Bartke. Thank you, Professor Strobel, that this has been achieved. Around 800 scientists and data specialists from 100 countries have registered. A large and worldwide competence meets in Salzburg to talk about one of the most valuable raw materials of today's digital world, data. Data is not only the basis for science and research, for analysis and decisions. Data is present everywhere in everyday life. The various apps on smartphones, navigation systems, weather forecasts or internet searches, health and sport applications, services in all areas of the economy and so on. Many things would not longer function without data technologies. Big data and data analytics are also increasingly shaping the business models of companies and young startups. The ability to use data effectively can mean the difference between success and failure for companies and organizations. The enormous growth in data volumes in the big data age also presents us with major challenges. Whether medicine, biology, or meteorology, whether agricultural sciences, mathematics, economics, or chemistry, all technical and scientific subjects generate an enormous volume of measured values, numbers, data, and information every day, and that worldwide. In order for researchers from all disciplines to have the best possible open access to this data and to be able to use it for research and development, there's a need for universally applicable standards for the collection, storage, use, dissemination, protection, and archiving of data. But it is also very important to take people along with us and put them at the center in the digital age. Digital humanism and data ethics should not be forgotten. People and their values should be at the center of technology development with all the enormous possibilities in the digital world. And it is important that research results also reach and are used in society and the economy through the transfer of know-how and innovation. And I think Salzburg is the best place to discuss this for the International Data Week 2023. Salzburg is a hotspot for data research in Austria. With our science and innovation strategy, Salzburg is ambitiously developing this hotspot further. With strong geoinformatics, data sciences, mathematics, and computer sciences, with data research laboratory, industrial informatics, we are well positioned at the University of Salzburg with a new faculty of digital and analytical sciences. The Salzburg Research Institute has also focused on IT and moving data with a focus on motion data intelligence and is working on solutions for the sports industry or mobility. Salzburg is also strong in the field of safety and security, for example, with the Center for Secure Energy Information Technology at the University of Applied Sciences. As a strong location for art and culture, a data arts forum is also being established at the Mozart University, where the focus is on artificial intelligence and the use of data in art. And we have a very good educational offer in the field of data, geoinformatics, artificial intelligence, and the Copernicus Masters Program, which provides for the next generations and talent. The province of Salzburg invests heavily in research, professorships, research centers, and research groups, but above all, many projects in the area of application research and implementation in practice have already been supported. Once again, a very warm welcome to Salzburg. I wish you all a successful Congress. Take your time to have a look to our beautiful city. I can assure you there is a life also outside the conference center. Come back soon, bring all your friends and family, and leave a lot of money here. Thank you, a very warm welcome.
Thank you, Mr. Governor. And also about this spending money, you don't have to spend too much money, but there is a special offer by Salzburg Congress that you can buy a 72-hour pass to most of the museums in Salzburg. And it's announced as you can use it while you're at the conference, but that doesn't make sense because at the conference, you're at the conference, right? We hope so. So I talked with a gentleman down there on the ground level and he said, no. You buy it while you're at the conference and you can still use it for 72 hours after the conference. It counts the hours start when you use it for the first time at some museum. So it's a splendid offer. Maybe you can work with your hotel and your airline to delay your return trip. So that's me on the picture there and Bernie Zagel. And we have agreed that I would open and Bernie will end. So we don't have too many people on stage at the same time. Why the two of us? When we started this whole endeavor of getting this great conference here, it was actually Sepp Strobel was also involved. And Sepp and I, we were approached by Salzburg Congress and Convention Center whether this conference, this splendid conference with these great folks from the international organization, whether this shouldn't be in Salzburg. Because we had started some initiatives here. We were the first university in Austria to offer programs in data science, in human-computer interaction, in the geosciences, and in geoinformatics, international programs. So it kind of made sense to have a conference when it was supposed to come to Europe at some point, to have it in Salzburg. I'm really proud that we were able to achieve that. And the topics, the first main topic that you see in the first keynote here, of course, is geospatial data science. That makes a lot of sense in the connection of the strengths we have here. Data ethics, which is also one of the main themes, and the governor just mentioned the humanities and the ethical part, has always been part of our data science master's program. It's mandatory in the program to talk about data ethics. Makes a lot of sense to also have it here right from the start. Inclusivity, anyways, the data and the global challenges. I just saw entering the head of our Doppler lab on using geospatial data for the humanities. Stefan Lang is also one of the vice deans of our college. Yes, back then when we started this initiative of getting the conference here and working out the topics and the themes, we didn't have the new faculty yet. In the meantime, we have founded a new faculty of digital and analytical sciences at our university. We have made a major structural reform and modernization of the university. And so you see these long titles. Also, we founded a new department of artificial intelligence and human interfaces where I'm at. That's data science and AI and also human computer interaction. And we already have this for a while, but one of the departments in our faculty is geoinformatics as well. So now we can say, now since the faculty has been founded, we can say, well, this faculty is sort of hosting the event, and it's, in a sense, it's a major kickoff also, international kickoff for our faculty. Let me go into one content point. What I've been noticing in the last years is that the field of data science and the very important aspect of data governance, they have kind of developed a little bit away from each other, but they need each other. You can't really do meaningful data governance without knowledge in data science, and data science also requires more smart data governance. And that's at every level. That's on the operative level where people have to collaborate, because we have very few people who are data scientists and data governance experts in the same person. So people have to collaborate in teams at the operational level, but also when we envision new data mesh. I think now people are talking about data mesh instead of data lakes or whatever were the buzzwords. So when we talk about the new data mesh, also folks have to envision this together. So this is one of my hopes for this conference, that people from these different areas talk to each other and find common grounds, get out of your own comfort zone. If you're a data governancist or a data scientist, please don't just go to your sessions, but also listen into the others and make it understandable to the folks from the other area. I know there's a lot of technical language in every one of these areas, so maybe a lot of acronyms, maybe try to make your work accessible to the others. I think for the future of this whole data area, making the best use of data with human-centered and making sense of data, I think we really need data governance and data science to work together very closely, very intensely. I come to the thanks before handing over to some other very fine folks here. I would like to thank our gold sponsor for this conference, which is the Copper Data, and one of the heads of Copper Data is sitting there, Philip Bear, three rows behind the governor. Copper Data is an independent software manufacturer that specializes in digitalization for the manufacturing industry and for the energy sector. And they have a software platform, Xenon, that enables users worldwide to automate, manage, monitor, integrate, and optimize machines, equipment, buildings, and power grids. And we're very grateful for the great support of Copper Data, not just for this event, but many other events of our faculty. Silver sponsor, the Salzburg AG. Well, probably the electricity here is supplied by Salzburg AG, because this company supplies Salzburg with electricity, water, telecommunications, public transport. The bus system, I think, as I know, as of now, right, still operated by Salzburg AG. There are some changes maybe. Anyways, almost 500,000 customers, and also supporting this conference. There is a hybridization sponsor, because as you know, we have a hybrid setting here for this conference. It's broadcast worldwide, and that is Chalmers eCommons. Chalmers eCommons, as our hybridization sponsor, is a gateway to a collection of local, national, and digital expert functions and resources. Of course, we need to thank Salzburg Congress and Salzburg Convention Bureau. Without them, we wouldn't have this conference here, and it's extremely professional, the whole setup. Our staff, I'm not going to mention individual names, and they would be way too embarrassed if they were mentioned. Maybe at the end we can do that, but obviously you have seen very friendly folks downstairs who have helped you. as you enter the building. The state and the city have been great supporters of our faculty, but also of this event. And as I said, the reception we have tonight, the music reception, is sponsored by them. And the 3 founding organizations. Without them, this whole conference would not exist. And yes, so I would like to invite you. I think the first one will be Bernd speaking here on behalf of CoData, Hillary from RDA, and David from WDS. But before I hand over the stage here to Bernd, let me thank you, because obviously without you being here, we wouldn't have this conference. Thank you for making the trip to Salzburg, and let me hand over to Bernd.
Thank you, Arne. And we have to change the slide. Should we do that? Yeah, there goes my first half minute. There's 2.5 minutes. Welcome to all of you, and thank you, Arne, for your kind words. What I would like to say today is that it seems that this year there's a lot of 5s and 10s. CoData is approaching 50 years. I've been president for 5 years, stepping down later this week, retiring as well very soon, but that's not so important. We have 10 years of RDA, of course, and believe it or not, in January, we already celebrate 10 years of FAIR. That's already 10 years. We also have a decadal program, so it's all about 10 years. So I really think that what we should do during this conference is not only look about what we're doing today, but really trying to look 10 years ahead, what's going to happen. And it's very difficult to predict the future, of course, except for stepping down. But what we know for sure is that we will be stuck for at least 10 years with the AI hype. Some universities even start a special department on AI, I understand. But at least this one has a human interface, which is very good. Because as people probably know, I'm very skeptical about what AI is. I think it's not AI at all. It's just pattern recognition. And computers are, of course, very good in stuff we are bad at, like the monk work, but there's no intelligence there at all. So we can debate that the rest of the week. I don't want to go into the details, but one thing is for sure, that AI models or any model are only as good as the data they are fed. So data is going to be even more important than in the past. And the governor said that's the most important asset, but one of the things we have been fighting for the last 5 years is there is no market, there is no pipelines, there is no infrastructure for data. We have to build that together. So indeed, please find each other, make sure we get all these data right there and make them what we now call fully AI ready, which is again fair, of course. So we really need to work together very strongly to gather the data and work on the data together. And we know what I mean there. So with that, it's a nice moment to hand over to Hillary, I think, and I wish you a great interaction during this conference. Thank you.
Thank you very much, Bernd. Good morning and welcome. It's my great honor to welcome you on behalf of the Research Data Alliance, a global organization. A handful are here. We have almost 14,000 members across the globe. And we have a vision that researchers and innovators can openly share and reuse data across technologies, across disciplines, and across countries to solve the grand challenges of society. And our mission is to build the social and technical bridges to enable that. And the bridge analogy is quite interesting because, Governor, I believe that if we didn't, the bridges are quite an important infrastructure in Salzburg. They connect the two sides of your beautiful city. And I'm sure there's a lot of maintenance and work to do around keeping them vibrant, accessible. They're all different and they're all very beautiful. I've had a lovely chance to walk around the town to see them. What these people in the room here and the many others that are not able to join us are building those technical bridges. They're building a digital infrastructure that is not as obvious and as concrete as the bridges, but is equally as important. And each of your roles and each of your contributions to this digital infrastructure, as Baron says, it's still a long way to go. We have a lot to build, but it's really fundamental. And we're very grateful to you for coming here today to spend the week and to interact together. And one of the wonderful things about IDW International Data Week, where the Research Data Alliance and the CoData and the World Data System come together, we organize our plenary meeting, which is very much a working meeting. CoData and WDS organize SciDataCon, which is a little more traditional that many of you will know if you like workshops and presentations. But they're so complementary. There's so much content. It's going to be a hard and long week. Of course, all the recordings are available, so that's part of the hybridization aspect. Even if you're physically present, you have access via Whova to all the recordings afterwards. So even if you have to go to one meeting and you have to miss another, you'll be able to follow up afterwards. But it really is a festival of data, and it's a festival of you. It's a festival of your work and the work that needs to be continued to do. So I really am very grateful to you for all coming here today. I'm so grateful to Arnie, Joseph, Bernd, and all the others from the team in Salzburg. I said to them last week, I'm not sure if they knew what they were taking on when they said they put their hand up and said they'd like to do IDW. It's a complex event to put together. It's like 3 or 4 events in one. But I think that it is worth it. And I'm grateful, very grateful to Simon from CoData, Meredith from WDS, and all their teams as well for the collaboration that we have together. I believe the participants get wonderful activities and content and take-homes and connections. So please build those technical bridges, but spend a lot of time building the social ones too. I wish you a wonderful conference, and I hope to interact with many of you during the week. Thank you.
Well, good morning, everyone. Governor, thank you for your words and introduction. Arnie, thank you. It's lovely to see everybody here, and I hope everybody online is actually having a good experience on the digital platform as well. So on behalf of the World Data System, I would just like to welcome all of you to this wonderful Festival of Data, IDW. And I say that on behalf of our 130 members. They are all sitting on treasure troves of data, these wonderful people that lead these fantastic scientific repositories around the world. The World Data System has brought along quite a few people to this meeting. We have the majority of our scientific committee here, which I chair, and we had a fabulous meeting yesterday with our colleagues to think about strategic issues going forward. And so we're looking forward to enjoying this meeting and using it as feedstock into future thinking about World Data System strategy, but also working in collaboration with the sister organizations that make up IDW. So in addition to our scientific committee, we've also got our International Program Officer Executive Director, Meredith Goins, and we have the International Technology Office Executive Director, Raina Jenkins here as well, and a number of the staff that work on programs and specific projects under those 2 offices. So that's quite an entourage, as it would be. We also have a number of our repository executive heads here from their institutions as well. So I want to just encourage you to find us and to interact with us and work with us. I think that Barend has got it absolutely right, that you know, artificial intelligence may not actually be all that intelligent, and it's certainly artificial. We have real live intelligences for you to interact in these fine people. And so I really do hope that you will find us all and talk to us. So we will be interacting with you finding you when you don't find us, and we really look forward to advancing the collaborative spirit of IDW and really thinking about the way that this event not only helps us within our respective organizations to do better within each of those, but also through collaboration to really advance the mission of thinking about the future of data, the future of science, and the future of what kind of workforce mobilization we can bring about through the data revolution to actually empower people to do new and exciting things with their lives. So thank you very much. The last before the closing speaker, I guess. So, or Arnie, I guess back to you. So thank you very much for being here and looking forward to a fantastic week.
And let me add that David is a very relaxed, very laid-back, fine gentleman who was our guinea pig yesterday, the first one who registered, and when all the systems, we start to figure out how it worked. Well, it's good that we did this yesterday because the long crowds today. So thank you also for that. Our staff was really happy. So we're done with the opening session. We're perfectly on time. And so thank you. And thanks, Mr. Governor. Thanks to Bernd, Hillary, and David for joining me here on stage. And we will immediately lead over to our first content session, scientific session on geospatial data science. And for that, I'm asking Bernd to take the stage together with the folks you have invited for this session.
Well, good morning, everybody. So let's start the data science part. I'll quickly ask for my slides and then also wish you a very warm welcome from my side to Salzburg and online, obviously. So what we're going to do today is that we are very much honored to kick off this session with an opening plenary that is called Spatial Data Science. Now, the idea is to discuss the entire myriad around why we think where is important and where matters. My name is Bernd Resch. I'm a professor for geoinformatics at the University of Salzburg and a visiting scholar at the Harvard University at the Center for Geographic Analysis. And I'm hosting this session together with Professor Strobel from the University of Salzburg, one of the pioneers of geoinformatics in Salzburg and worldwide. Good, so you see the panel already. We're going to introduce them in a bit in more detail. We're very much honored. Thanks for agreeing to joining us here on the stage. Linda Beal from Esri, Professor Christoph Janovic from University of Vienna and UCSB in California, Dr. Anita Graser from Austrian Institute of Technology, and Getachew Geller from the Christian Doppel Laboratory for Geohumanitarian Action here at the University of Salzburg. Good. So how are we gonna go through these 1.5 hours that we have? First of all, quick introduction and scoping. I'm gonna be done with this within, I don't know, let's say 5 to 7 minutes. The keynote of the session will be held by Linda Beal, and after that, we're gonna have a few very short, lightning, inspirational talks by the other panelists, and then we go directly into the plenary discussion. We're gonna alternate between questions from the online audience and the on-site audience. We have microphones in the room. Good. Quick wrap-up and summary in the end, of course. So why do we think that spatially special? And that's the keynote talk of Linda Beal. This is data that we deal with. Data science as we see it every day. On the top left, we, for example, see this time series of COVID-19 cases and deaths in the US in this case, standard timeline that we know. We have a number of images, in this case, refugee camps, in this case, refugees moving along the countryside. We have images where people are canoeing and kayaking through the streets. So obviously a quite severe flood has hit. And then we have different kinds of other raw data, which could be this, 27.3 degrees Celsius, a measurement value, ambient temperature. We have these kinds of things that we know in terms of, in the worst case, an Excel sheet, in the better case, a relational database. And then we have different kinds of exploratory outputs as well. scatter plots, correlations between variables, all different kinds of things that we see. And then, of course, finally, we have this confusion matrix-like thingies. And artificial intelligence is not the answer to everything, as we heard before. And I'm always a big proponent of stating that the confusion matrix does not explain everything that we actually want to see. Meaning, confusion matrix itself, false positives, false negatives, true and false positives, means that we statistically analyze how an artificial intelligence model or machine learning model performs. Now, in the end, if we go a few steps further, this may not necessarily tell us how well we actually understand or research the problem under investigation. And that's the key thing here. Now, let me bring up a very old quote, which is this. Data, in the end, and that's the conclusion, are not just numbers. They are numbers with a context. And in data analysis, context provides meaning. And that's the key conclusion. Now let's add this context from a spatial viewpoint. That's the output in the end that we see not only from a cartographic viewpoint, not from a map viewpoint, but even more so from an understanding and knowledge viewpoint represented in map or map-like visualizations. So for example, here on the top left, we see in these red shades, areas that would be very strongly affected by a natural disaster. Here we would see COVID-19 hotspots and predictions for those 2 weeks ahead of time. Policymaking, right? At some point, if you only have time series, which kinds of policies do you enact where? And here we have this fine-grained visualization. Down here, putting what we saw before, refugee camps on the map, on the globe, so to say, and into spatial context, densities of dwellings, densities of people living in these dwellings. Here, company networks as observed through connections in digital space. So one time through URL connections, hyperlinks, one time through connections on social media, and we see hotspots, so to say, of innovation in different cities, in this case, Berlin, Germany. Then, of course, in this case, hotspots of bikeability, very different application in the city of Boston. And then down there, and that's the key conclusion, these 27.3 degrees Celsius, if we put them on a map, if we put this time series and connect them to a map position, we know where things are happening and can interpret accordingly. And then, of course, there are these map-like or non-map geographic or inherently geographic visualizations, like this chord diagram, in this case, refugee movements between different countries and cities. Good. So this is the central idea. Spatial obviously matters to some degree. We're able to put things into context to better understand where things happen through spatial data science. And with this, I would like to hand over to Professor Strobel to introduce the keynote by Linda Beal. Thank you.
Thank you, Bernd, for setting the stage in more than just one way. And I truly believe the main keyword you have been mentioning was context. Data don't have a lot of value outside of context. They're the foundation for decisions. And when I was watching all of you entering this room today, you were not selecting your seat in a random way, right? So obviously, you were coming in the door and assessing the spatial setting here, and you either were going straight for the first row because you had something to do in that session, or you were holding back and starting filling the room from the back, or you were chasing friends and clustering around these. So very clearly, as we say, whatever happens, it happens somewhere. And data without spatial context isn't really what helps with those decisions we need to take. I'm very glad to welcome Linda Beal. She's currently the ESWA Program Manager for Spatial Analytics, and that's essentially this commonality, this joint area of interest we've been sharing for many, many years. She completed a master's in GIS, a PhD in spatial and statistical modeling. Following that, with quite a few years at Imperial College London, where she established herself as specialist in biostatistics, in spatial epidemiology, essentially focusing on data science in health and Some of you might be familiar with the UK Environmental Health Atlas. This is one of the outstanding and milestone products, which, yeah, it's one of your claims to fame, I would say. What I was really happy to see that, Linda, you're listing your current focus, area of focus, as the development of geovisual analytics and usage of AI in geospatial analysis. And the one phrase I'd like to underscore right here is the geovisual analytics, because that means there is people in the loop. There is humans in the loop in there. Following up on what the society's representatives have been saying, we need intelligence, and there is still a very strong case to be made for the human intelligence coming in here as well. But with that, I'd be happy to hand it over to you, Linda. Take it away from here.
Thank you very much for the introduction, and thank you to the organizing committee for inviting me. So I want to start right with that question of, is spatial special? This is something that you may have heard talk about. It's something that's very often discussed within the spatial world. And if we're looking at this and we're looking at the actual meaning of what spatial is it different from what's usual? Is it something that's out of the ordinary? Well, I would say that maybe it's not. Spatial data is something that has occurred at a location. It has occurred somewhere. Is that something that's really unusual? Something that's really out of the ordinary? So no, I'm going to say that spatial is not special. Spatial is absolutely crucial. It's fundamental to work that we do. And it's something that should always be considered in analysis. So there is this process of analysis that has sort of historically happened in that you have your question, you collect your data, and you think about the questions and the hypotheses that you're going to ask. Well, I would say that nowadays, in the sort of the wider context of doing research and analysis, that's actually been flipped. What's happening is we're collecting data. We're automatically collecting data, and the data scientist and the spatial data scientist is being asked to find what they can out of that data. So you need to know, as the spatial data scientist, what you can pull from that data. You need to be able to see all of that data and know what questions you can get from that data. So data comes in many different types. You know, you can have structured, unstructured, big data, but actually when you look at the data itself, however it's stored, be it, you know, a database or a large store, what type of different data are there? We can break that down into 4 fundamental types. So there's text data, there's numeric data, there's date time, and then there's binary, there's Boolean data. Now I'm going to say that we all need to remember a 5th one, the spatial, that is also in the data. And I've done a really extensive and deep scientific study to see if we can actually fit all 5 pieces of data in our mind. And you'll be pleased to see that we can. There's even room for other things. So there's no excuse for us to not consider all of it. Would you think it's okay if in your database or your Excel spreadsheet that you only work with integers? I mean, let's just drop off those additional numbers after the decimal. They're not that important. You're going to say, no, that makes a huge difference. So I'm going to say back to you, why would you drop off that spatial component of your data? Why would you not consider that in your analysis? There's also this discussion about how much spatial data there is. And there's been this traditional rule that 80% of data is spatial. Nobody really knows quite where that's actually come from, who originally said that, whether we're making this up to be special about our spatial data. Well, fortunately, the US Open Data Site actually says how many data sets it has available and how many of them are geospatial. And that comes out at around 77%. So whoever said it was pretty spot on. There's also a lot of names for spatial analysis. You know, you'll hear lots of different departments. We've already heard some of them this morning. It doesn't matter what it's called. It's not important what the name is. It's not even important what software you use. We'll have our choice of software. There's different types. We use different types. We will jump between different software. But what's important is the difference between the software and the science. And most importantly, that you consider that spatial component in your data. So I don't want to ring fence it and call it special. It's something that we can all do. So if you're willing and able, and you can do this remotely as well, I'd like you to raise your hand if you do some kind of statistics in your day job. So that could be something like machine learning, regression. You could be just finding the average. Do you find the mean, the median? Okay, we're all doing some kind of statistics. Keep your hands up. Now, I'd like you to put your hands down if you call yourself a statistician. Oh, okay, there's a lot of us still with our hands up. Okay, you can put your hands down now. So you don't have to be an expert to use something, to think about it. Okay, there's limits. We might not all do really advanced statistics, but we all use a little piece of it. So I want to encourage you all to use a little piece of spatial. And I'm going to try and persuade you now why, what you're going to get out of that. How can it help you? So tabular data, it's getting bigger and bigger. Can we scan through that and see what the problems are in that data, get a really good sense of that data? No. No, of course, we're going to do some kind of exploratory analysis. We're going to do a count. We're going to find the mean, the median, the average. We're going to get a distribution. We're going to look for outliers. So we're going to get a good sense of that. But let me show you an example of something that we did when I was at Imperial. This was a many-year study looking at the with possible impact on cell phone towers and childhood cancers. So there was a big team of us. There was spatial epidemiologists, there were doctors, there was epidemiologists, there were statisticians, and there was a spatial data scientist. So we gathered all of the data from the National Health Service and from all the mobile phone, cell phone towers companies that there were. At the time, there was 4 of them. So you'll see as this video is scanning through, I mapped the data. That's what I do. Now I've circled a piece there and you'll watch it as it goes through these different companies, and you will see that one of those companies, who shall remain nameless, missed out one of the areas. Easily done. There were a lot of different regions. Each one gathered it, sent it to a central place, sent us this very large data set. Now, this was a very serious paper that we were writing for the British Medical Journal, appeared on the BBC News. Imagine if we'd have missed a whole area. We only saw that because we put it on a map. Very simple thing to do. So maps are really powerful. They draw people in, and they can be used to engage your audience. So this is a map of population density across Austria. Now, probably a lot of you are already looking at that thinking, hang on, there's bits missing on there. And if any of you live in those places, you're probably a little bit upset. I apologize. It was a random choice of places, but I wanted to make the point of how powerful that map is and how nobody wants to be missed off the map. So use that. When somebody doesn't want to give you their data, show them the map when they're not on it and everyone else is. You'll be impressed how quickly they send you that data. So when we work spatially and when you work non-spatially, you will find a lot of your data is aggregated into boundaries. So we don't live within boundaries, but this is how our data is aggregated so that we can deal with it, and also that so that we don't break any kind of ethical reasons. We may not be wanting our individual information to be shared. We aggregate up that data. This has a major impact on all of the analysis, and it doesn't matter whether you're doing spatial analysis or not. So the first thing on the maps, I said maps are powerful. Well, if we're working with the aggregated data, we need to decide how to classify that data. So this is showing unemployment, and this is using natural breaks. And what that's doing is finding where there are significant statistical gaps, breaks within that data. This is using 5 classes. This is using 8 classes. Very different looking map, both correct. I could also use equal interval classification. I'm using equal bands based on the range of that data that I want to then show my data to be binned in, to be classified in. Or I could use quantiles. Now I'm breaking my data up so there's equal amounts of data within each of these 5 classes. Completely correct map. It was my choice as the map maker, and I am trying to show you something specific. So next time you see a map, look at the legend. What are they actually showing you on that map? Read it carefully. So just be aware of how they can be useful and how they can allow people to be persuaded. So another thing I want to mention is something called the Modifier Area Unit, or MORP. Now, this was first outlined back in 1934, so it's not a new thing. And what this does is as you aggregate your data into different aggregation areas, so whether you're going into municipalities or districts in this case, your data is actually different. Even though individually it's the same data, we're putting them into different size units in this case, so that's the scale effect. And what we see, of course, the numbers are different. We'd expect that. Municipalities are relatively small, districts are a little bit larger. So we expect the numbers to change, but did you expect the location of where there's the high and the low to completely change? I just picked one data set. I didn't spend hours looking for one that would show this. The first one I picked, percentage of unemployment. Again, it's not wrong, but remember your analysis is only relevant to the scale at which you did your analysis. So the second effect is what's called the zonal effect. And that's the same size boundaries, but just different shapes. So it's aggregating those numbers in a different way. And what this does is it impacts the statistics as you're doing it. So this is just the first raw numbers that I'm showing here on a regression. Each time that relationship between, in this case, we're looking at education and unemployment, they're all the same relationship, but the numbers vary considerably between 0.6 and I think 0.8. That's a big difference by the time you've put multiple different variables together. And in some cases, the direction of that relationship can completely change. So perhaps you should run your analysis at different scale. So reliable population data is pretty much essential in many pieces of work analysis. It's the denominator that we use, because what we're doing is we're looking to see who's been impacted. It doesn't matter what you're studying. It doesn't matter what you're working in. So it could be business, crime, health, transport, property, all of those things are considering people. Otherwise, we're just mapping and we're just looking at, analyzing, studying, and showing where there's more people. It's not necessarily what we want to do. Population data is collected at census. Census in many countries is every 10 years. Some countries every 5 years. As you move away from that, it's going to get less accurate. And spatially, that accuracy is not the same. So some cities have built a new housing area, brought in some younger population. The demographic in that area is completely different to the one that the census had. So it's not spatially the same. There's a variation across all of that area. And also we move, and the boundaries move. So where we draw those census areas changes at each census. So what one means 1 year, 10 years, or 5 years later is a different boundary. So all of those things can and absolutely should be considered during your analysis, even if you do nothing spatial with it at all. It's all impacting your analysis. But there are some unique things about spatial. There are some special things. So very quickly, I want to go through the geometric properties, the topological properties, and joining data. So I've just picked out what I consider to be the 3 key things that are special about spatial. So the first thing that a lot of geographic systems, software, and even analysis that we do is based on Tobler's first law of geography. And that says that all things are related to everything else, but near things are more related than those things that are far apart. So proximity becomes very important in our analysis. So let me show you how even just a simple thing like using distance can actually give some real information. So this is showing the estimated time of arrival of ambulance and how quickly people get to the hospital in some work that I did in Hungary. It shows that the mortality risk significantly increases after about 15 minutes for strokes and 50 minutes for heart attacks. Now, if they go to a specialist center, there's less of them. They have to travel further. But because they're specialist centers, we found that the mortality risk increases for both within 60 to 70 minutes. That's a big difference. So in the short term, that gave an information to ambulance driver. In the longer term, that influences policy. So topology, we're talking about adjacency, who's near, containment, what's inside, and connectivity. So within and neighboring features. So these again can be used for a very simple thing, or I wanted to show you something that's a little bit more advanced in what we can do. So this is going back to the health atlas that I worked on, and we used hierarchical Bayesian analysis to estimate rates and risks for 25 years of multiple different cancers across the country. Some cancers are fortunately very rare, but what that means numerically is you have statistical instability. So what we can do is we can borrow information from nearby areas. Going back to that idea I said about Tobler's law, near things are likely to be more similar than things that are further apart. Interpolation is something that we can do using spatial data. Again, we're using that same thing. Near things are more likely to be similar than further things apart. So we can sample things at random locations, and then at the places where we don't know the information, we can estimate that value. So we're not going to collect soil samples every single place there is on the earth. We don't collect weather everywhere. We interpolate between those 2 areas. Now here we're seeing different maps of NO2, so air pollution from traffic and industry, and you can see the shift that we've done in the science over time. So the black and white ones are using earlier methods, and they're showing just that central area within the ring road, and then we using Kriging methods, and then more recently combining Kriging and regression, we can actually improve those results that we get. And all of these are using spatial data science. And what difference does that make? Well, if we take that up to a European scale and we look at the EU guidelines as to whether they've actually met those guidelines or not, we see that difference between using the nearest monitor, so just using distance, still some spatial analysis, then moving on to doing some kind of interpolation. We see the variation in the EU population is between 6 and 12% above the guidelines. That's a big difference in numbers across the EU. So the last thing I want to talk about is joining data. So most of you will probably have used some kind of joining data, which is easy to do if it's been collected as part of that same analysis. It will have something in common. It will have a field that is similar, and you can join on that. But what if it's data that's not been collected for a single purpose? How can you join that data? Well, if it has location, you can join it using location. There's no need to standardize on fields. So the examples I'm talking about just now about who's exposed to pollution, they're a completely different thing. The same authorities do not collect population data and pollution data, but we needed to analyze them together. So then we can really expand our knowledge. So we can grow out and we can do that type of analysis that's saying who's been affected, what's their health outcomes in the work that I've done between both the physical and the social environment and health outcomes. But there are so many other opportunities out there. Imagine the ability to bring together data that has never been previously analyzed together, just because it had no fields in common. But using spatial data, of which 80% of the data has, you can now bring those different data sets together. And our lives are very intertwined. Our topics are very intertwined, but you can analyze those things together. So spatial matters. It's the context in which all events occur. We can use spatial to consider which policies have been successful in similar places. We can determine inequalities. Different places may be at different stages. They may be at different stages in development. Some may have had policies implemented and not. We can learn from the past so that we can improve the future. And although boundaries are arbitrary, they are often how we actually have our interventions, our policy. So it does make some sense to work with them. So the last thing I'd say, there are some special things about data, but we don't have to be spatial data scientists to use it. I think spatial and geospatial science is very much a bridging discipline. We've heard the word already today about bridges and bridging things. I think spatial data can be that bridging discipline. Spatial data scientists are able to look at the whole picture. They're essentially able to zoom out and see, and they bring valuable skills to many projects. But spatial should be considered by all data scientists. Know your limits. Know at what point you need to work with a spatial data scientist. We've heard about interdisciplinary. I think that's really where the power in all our work comes from. And that's how we do our best work, respecting each other's specialities, but considering all of them in your work. Thank you very much.
Thank you, Linda. And thanks for bringing up my preferred and very special tool, my favorite tool, which is joining by location, which is not only a tool, but kind of a programmatic statement sometimes as well. We will now switch over to the panel, and having learned that what we have just been able to follow, it's not only about what is where, but much more about why is it there and why do we care? And I believe that progression with handling spatial information might be news to some, but I'm very glad that we now have a panel being able to bringing in some complementary aspects, challenges, and that'll be the foundation for a bit of discussion as well. Over to you, Bernd.
Well, thank you, Sepp. For me, it's just about to introduce our first panelist, which is Getachew Geller from the Distant Double Laboratory for Geohumanitarian Action here at the University of Salzburg. The stage is yours.
Thank you. I think I'm a bit short. Okay. I'm going to speak on integration of AI with Earth observation for building extraction in forcibly displaced population settlement areas, and then to show what prospects and challenges we have. I don't know whether any of you know the statistics. Now at this moment, according to UNHCR statistics, almost we have more than 108 million people displaced from their homeland. Of these, almost more than half of them are staying inside their national boundary, which we call them IDPs. And then the rest of them are crossing international borders and staying in the refugee camps. The shocking news always when I see this thing is the trend is still increasing. And then why we need this information, why we want to map, why we want to monitor FDP settlement areas is, it's very important for two things. One, for the people who are going to the field to know where these people are. The second thing is the information is very relevant for non-government organizations, aid organizations who are supporting or providing aid or life-saving services for displaced people. And so what we are working is not only for scientific curiosity, but also we have a purpose to serve at the end of the day. So after that, what I want to say is, well, to monitor FDP settlement areas, Earth observation is providing spatially explicit and temporally frequent information. For the last 2 decades, huge amount of expertise has been invested to monitor various aspects of FDP diets. For example, from understanding the environmental change toward discounting individual houses and estimating house density, number of residing population. So the information is very relevant, expertise is there. Now with this era, AI is coming with a new opportunity, an opportunity of automation. So it's possible to count, localize, detect, segment, classify Earth observation images and detect dwellings and houses in FDP settlement areas, as you can see. But AI is something, push the button and easy to go when someone is working on Earth observation imagery. Here, I would like to pinpoint, there are people who are working on computer vision and application of AI, deep learning, and the rest of the things on natural images. But Earth observation is a bit complex than natural images, which needs a little different perspective. So I would like to emphasize on things which are tailored for our problem, at the same time which are generic for people who are working in the integration of AI with Earth observation. I would start from a very static problem, which is computational resource. I don't want to focus on this because once someone has a good pocket, it can be fulfilled. It's not a dynamic problem. The second problem is inherent characteristics of targets we are detecting. And then it goes to the data characteristics in terms of amount, quality, and then the main issue or the centerpiece of my talk goes into transferability of AI models across space and time. Let's first start from the data. And I took this note from recently published an article and title is there. Interested people can read on it. Now, we don't have shortage of image, I will say, as per my perspective, because there is voracious and huge amount of data is coming from space. But the problem is this image is fit for purpose for objects we are detecting? The second thing is we have events. For example, FDP settlements areas are evolving somewhere. Is the timing is nice, or is it synchronized with the event to detect these targets? The main important issue, which is also raised in other speakers, is do we have ground truth data? Because if we fed AI models with curated data, it's established reality, you can get good results. But now the problem is we don't have a data. At this time, one could say, why not you go for the crowdsourced information? So if we go with the crowdsourced information, always it comes with a quality issue. So now we should make a trade-off. Should we spend a lot of time on cleaning our data and training our models? If someone who is working on operational emergency response may ask me, well, if I invest this amount of time cleaning my data and if training my model and come up with some accuracy, and then where is its efficiency? And then as you can see, if we train our models with less quality data, the results are quite expected. It's not quite sharp enough. The other thing is inherent characteristics of buildings we are detecting. You know, because geography matters, as this is also the theme of the entire speak. When we go from different geography, houses or buildings can be made from different objects, maybe from wood, maybe from mud, maybe from others. And then they are quite diverse. For example, if you see in the middle of here, it's quite hard even for manually to see where are the dwellings. And then others can, for example, if you see here, are completely similar with the background. And the third thing, if you see there, they're quite spectrally diverse, but we don't know even where is the boundary between adjacent houses. That's a problem. I want to make two notes here. The first thing is, if one training model here, because we don't have data always, we want to use a trained model skill, and if we want to predict here, the models are not transferable. Why? Because the data distributions are quite different. The second thing is, if we want to detect, I don't know whether it's visible for you here, we have only, the model has detected only bright dwellings. The rest are light because they look like the ground. So this is one of the problems. Finally, I want to make a note. In combining Earth observation with AI, we should look into solutions that should be fast, because the time required to generate information to feed in the decision table is quite short, maybe 1 day, maybe 2 days. The second thing is it should be efficient in terms of resource, efficient in terms of annotations or data demand. And the third one is it should be transferable across space and time. And that means we need a more generic models which are smart enough to see targets which are different from place to place and time to time. And finally, if we want to bring all the solutions into the operational setting, they should be easy to use. Because there might be complex algorithms, but if they are not easy to use, at the end of the day, it's not going to serve the purpose. Thank you so much for listening, and thank you for the supporters of our research, and thank you so much.
Thank you, guys. This was a very good start. And you see that image analysis in data science and AI does not always mean discerning cats from dogs, but there are real world objects in geographic space that obviously matter. Good. With this, I would like to hand over to Dr. Anita Graser from Austrian Institute of Technology.
Thank you, Ben. And thank you for giving me this opportunity to talk a bit about my favorite data type, and that is trajectory data. I actually put the subtitle in putting the temporal in spatial data science, but we already had a reference to the temporal dimension as well. So I'm really glad that this ties in so well. Obviously, trajectories are not just restricted to geographic space. And I've brought you here a couple of examples from the really obvious and well-known and very pretty to look at examples of, for example, airplane trajectories that we can map to understand different patterns, holding patterns and behaviors, to more abstract movements in virtual space. For example, if you do eye tracking studies, you also follow the gaze of the person and its movement in pixel space, screen space. Then there's a lot of researchers who do sports analytics, and also there they are tracking movement in local space, for example, on a soccer field. And we don't even need to stay on our Earth. Like right now, there are rovers, there are helicopters on other planets, like the Mars rover and its helicopter buddy. And they are also being tracked, and people are following them around and making daily map updates of where they are going and how they are doing. So movement data analytics is not just spatial data science, not just geographic data science, but it really appears everywhere. But there is a couple of challenges that we are still struggling with, right? Movement data describes often very complex phenomena. So you can look at it in different temporal scales, you can look at it at different spatial scales. Sometimes you are only interested in one moving object, sometimes you are interested in how they interact with each other and how they are interacting with their environment. So all this means you have to integrate data from different sources, you have to be able to look at it from different sides in different scales. It is highly context and scale dependent, all the outputs that we are generating. We already heard about the modifiable areal unit problem. There's also a modifiable temporal unit problem here, which makes it slightly more challenging. And we also have the issue of spatial and temporal and even attribute uncertainty. So this could be, we all know that GPS locationing is not always perfect. You can see it on your own phone. If you try to find your way, it sometimes puts you in a wrong place. Other data sources like the mobile phone data, for example, will just put you to one antenna. So that means that your knowledge about the location of someone is at best tied to how dense these antennas are distributed in a certain space. So all of this comes together, and we need tools to be able to support the data scientists in working with this data. And there is where we still face a lot of struggles, because there are very few established tools and best practices for working with different data sets. So everyone is now trying to build something and to perform trajectory analytics, and I'm one of those people who's trying to do this. I'm the core developer of the Moving Pandas library, which aims to bring a very flexible trajectory analytics tool to data scientists in the Python world. And in these examples, you can see how I'm trying to build something that is not just working in geographic space. For example, if you want to look at migrating birds, like these gulls that go from Africa to Scandinavia every year. But the tool that would also work if you're just working with trajectories extracted from local imagery, like these cycling data from Copenhagen, or if you're into sports analytics, just reference to a soccer field. Because many of the things are transferable if you really look into it. But there's also some challenges that I don't want to just gloss over, but that I want to raise as a starting point for our discussion. And one key challenge is privacy. And it's particularly a problem for movement data, as I'm sure you will imagine. I don't know how many of you have heard about the New York City taxi ride data that was made public, I think around 2014. They thought they did everything right. They just published the pickup and the drop-off times and locations, the amounts that were paid for the fare, and the tips, and then they anonymized the taxi medallion number, so the ID of the taxi. There is no customer data. There is no, they thought it was impossible to reconstruct how much a taxi driver was earning. But of course, yeah, it didn't quite turn out that way. Even if there is no information about the customer, as soon as you spot someone in a real space, as soon as you know where they live, of course you could find out when they were picked up, where they went afterwards. And a lot of celebrities have been, trips have been reconstructed like this. And even if you're more opportunistic and you don't know exactly whom you want to follow or where they live, you can do some reverse engineering. There was this really interesting blog post about they identified a certain location that people don't necessarily want to advertise that they go to. It was some gentleman's club that maybe the wife or whoever should not know about. And then they reconstructed where are the regular pickups going to this gentleman's club on a regular basis. And yeah, it's the yellow dots here on the map, and there's an interactive map you can zoom into, and maybe you can find out who's living there. So yeah, anonymizing movement data is tricky. I was thinking of putting here a Ghostbusters reference, like who you're gonna call if you have to work with movement data. Your friendly neighborhood spatial data scientist, because we don't want you to make the mistakes that we have already made in the past. Come to us, I hope we can work together. Thank you.
Thank you, Anita, especially for quickly touching upon this very important concept that's oftentimes forgotten. Like in spatial data science, we would talk about location privacy or geo-privacy. So not, or a very different type and a very specific type of privacy. There is this paper from 2013 that says, if you give me 4 random positions of your mobile phone's day, I'm gonna tell you with a 92 to 93% accuracy who you are. And that's only from the location. And then, of course, merged with other pieces of data. Good, thank you. And with this, I would hand over to our last panelist, which is Professor Krzysztof Janowicz from University of California, Santa Barbara, and University of Vienna. Welcome.
Okay, that was one too fast. Okay. So I only have 5 minutes. I'm going to make this quick. I would like to talk a little bit about knowledge graphs and what role they play in analyzing geographic data. So we already heard that spatial data is special. I'm going to give you my take on this. I think you heard a wonderful statistical or procedural definition of that. I'm going to start with an information theoretical one that I like a lot, namely spatial data is special because on average, a sample of geographic information has less than expected information. And I think that summarizes many of the things that you heard before. But there's a whole breadth of other reasons why spatial data is really special that comes from the realm of data cultures that is not mentioned on many of the slides that you hear or see when we talk about why spatial data is so special. Namely, geographic data lives in this world of different layers. You have the boundaries layer here, you have the land cover layer here, you have, for instance, trajectory data that we saw before and so on. And all these layers can also live in different data modes. You can have text, you can have video, you can have imagery, you can have increasingly sound. So geographic data is multimodal. It's also multi-layered, as I said before, across physical geography, human geography, medical issues that we heard before and so on. But now come the really hard things to deal with when you are outside the spatial scope or the realm of spatial methods. Namely, geographic data or spatial data is also multi-perspective data. So we have multiple viewpoints on the same geographic reality. And people, as people do, don't often agree. And that's not an issue of being right or wrong. It's an issue of having different perspectives. One very common example is that there are different borders between India, China, and Pakistan when it comes to the Kashmir region. No single one of them is correct, so to speak. They come from different perspectives. If we move into cultural issues, discussing poverty, democracy, it gets even more complicated. Then geospatial or spatial data is also spatial temporally scoped. What is true today may not be true tomorrow. And what is true here, for instance, in Austria, may not be true, for instance, in Poland or the United States. So the validity of your data is scoped by space and time. And then the same is also true for different schemata. So not only for the data itself, but also the classes that we form. They simply mean different things in different regions. Oh, and by the way, one note that I also wanted to make, and I hope that is a good discussion starter, is that one part of what you are seeing here and what you saw in the talks here is talking about AI methods for geographic application areas. But there's a second part, namely what we call GeoAI, and that thinks also about this not as a one-way street, about how can geoscientists, social scientists, ecologists use AI tools, but also what do we as geo folks contribute to the broader AI society, AI community, and maybe that's something for our discussions. So Now to the knowledge graph. To make one more provocative statement, I believe that knowledge is a graph. The way we think is all about the connections we make when we went there somewhere, what happened somewhere, why one region was more affected by a disaster like a storm than the other one, who we met, when we met them, and so on. And one technology that is able to represent data, one novel technology, are such knowledge graphs. They are a web-scale paradigm for representing data, not just geospatial data, and for reasoning about data. And the reason why I think they're particularly interested in our realm here, interesting in our realm of spatial or geospatial geographic information, is because they fulfill many of the requirements from this data culture slide that I showed you before. For instance, knowledge graphs can deal with multimodal data. Even more importantly, one thing that I'm still missing in all our data discussions, data infrastructures, is that we have become very, very good at sharing data layer by layer by layer. You can go to your favorite data infrastructure and you can download layer by layer there, bring them into your analytical environment. This may be R, this may be Python, this may be a geographic information system. But then you do all your magic in there. You essentially create connections between those data layers that you saw on the previous slide, between boundaries, for instance, and unemployment, as we heard in the keynote. But then we never share those links back. We still live in a model from the 80s of layer by layer by layer that you download. Then you do all the data science magic, and then you're saying, but I'm not going to tell you. And then somebody else is going to, again, download data layer by data layer. Knowledge graphs create a dense network across these data layers. They also support multiple views, and they have a built-in way called open world assumption and other terms come to mind that allow you to handle knowledge that is locally consistent, but can be globally inconsistent, and you can still draw inferences on that. Very different than the slogan that we all grew up with from machine learning, garbage in, garbage out. Well, all data is garbage without context, without multiple geographic perspectives and so on. So dealing with inconsistencies in data is very important. Knowledge graphs also have ways to scope data spatial temporally. We can rather easily say that something is true here, but may not be true somewhere else. They also give us a language by which we can align different views on the schema level on the world. We can talk, for instance, to people that have different conceptualizations of terms like forest. You have all dealt with forests in your databases, comma-separated value files or whatnot. Maybe you don't know that there are 900 different legally binding definitions of forest. How do you deal with that when you would like to study deforestation, for instance? Well, knowledge graphs are fair by design. Most fair-based infrastructures are knowledge graph-based. And one of my favorite points, and that's the last one I'm going to make, in this time of data analytics and data science, we don't yet have a really good, at least in industry, feedback mechanism, what to do with the learning, so the results of our models, to make them feed back into our own data pipelines. In knowledge graphs and in graph learning, for instance, in knowledge graph embeddings, when you learn something from the graph, the product of this learning is again part of a graph, a subgraph or a statement in a graph. Thereby you create a denser and denser graph that is then better suited for your next predictions. If you like to check out one knowledge graph, check out the nowhere graph. That's our graph, one of the largest knowledge graphs in existence. 13 to 15 billion statements strong of geographic information across 30 different data layers. Thank you so much for your attention.
Good. Could I have quickly my slides back, please? So thanks, Jana, very much. Reminds me a lot of the semantic web when we discussed that like 15 years ago, right? Let's see where this goes in the discussion as well. So what we would like to do right now is to kick off the panel discussion with questions from your side. We're going to start with a quick question then from the audience. Can I quickly, thank you. and then cycle around, so to say. Now, by the way, this is an image that I generated yesterday using Leonardo AI. You see down there that you have to be very specific in defining what you want to see on the generated image, but it doesn't look so bad, actually. I mean, let's say the hallway is not too, it's very well hit, actually. Second thing is, there is even a map when we talk about spatial data science in the assignment, so to say. So this is what we're gonna do today, that we're just gonna challenge, I hope, the participants here. So I feel we've been preaching to the choir a little bit. So please feel free to critically see through and question the statements of the audience. Now, for the on-site audience, there are microphones, standing microphones over here and over there. If you have a question, please at some point start moving towards those microphones. Nobody will hand you them. Good. Hello. The microphone doesn't work. Seems like this one doesn't either. I'm gonna have a very quick question because Krzysztof Janowicz likes definitions and information theory a lot. So we're at a spatial data science conference or a data science conference. Now you write papers about GeoAI. So what's the difference between spatial data science and GeoAI from this point of view until we get the microphones working?
Does it work? Does it work now? Yes, okay, so that does the trick, right? Okay, so what's the difference between data science and GeoAI? Well, I would just say that spatial data science is a subfield of data science that is concerned with spatial temporal information, not just geospatial or geographic information. For instance, a lot of the work that we are doing is with architects, people who do physics, people that do urban studies, even people that do religious studies. And what is GeoAI? Well, GeoAI is both AI for geo, so people using AI techniques to help or solve problems in the realm of environmental science, geography, seismology, whatever your work area is. But GeoAI is also studying spatial explicit methods and making sure that they inform the broader AI community. So for instance, one key thing in the machine learning community are biases. And one of the ways to de-bias data that is very commonly used in the industry or also in academia are spatial methods. For instance, the modifiable area unit problem, or trying to understand how geo-representative data are. So GeoAI also feeds back to the broader AI community.
That makes a lot of sense. Thank you. So just for this terminological clarification, I see there is a question from the audience.
You're talking about me who couldn't find the right mic, right? Thank you very much for this excellent panel. My name is Claudia Medeiros. I'm from Brazil, and I've worked a lot with geospatial data. But recently, I've been talking with and working with people who are worried about virtual spaces such as gaming and places to better kill a dragon and things like that. So this sounds funny, but it involves millions of people and millions or billions of dollars or whatever. So I wonder whether you've had experience with this and whether some of the techniques that you've described could map into imaginary virtual worlds. Thank you.
Does anyone feel like you want to take the stage? Linda, from a broad perspective?
No? No? Yes? Okay, perfect. So I think there is a lot of shared knowledge between the two in the sense that we should be learning from each other. I think so far they've kind of kept apart in terms of the technology. So I would say that geospatial certainly needs to learn from the technology of gaming, whereas I do think that gaming is actually teaching people to move around in space. So it's certainly teaching the importance of that. So I think there is an overlap. I mean, you know, whatever engages people to understand about the importance of space, I think is only a good thing. But I think there's definitely a need for the technology on the geospatial side to jump in. We've heard about the problems with trajectories. Actually, they've kind of solved that within the gaming industry a little bit better. So there's room for us to work together, I would say.
Thank you, Linda. And there would be a follow-up question from the online audience, which says, why can geographic coordinates not just be treated as another attribute in a multidimensional or multimodal data space? That's what you mentioned before, Jano, as well. Perhaps a concrete question in the area of trajectories and mobility data.
Yeah, that's an excellent question that we, of course, hear a lot. Why can't we just deal with latitude and longitude like some other float values in our database? Wouldn't that be fun? Yeah, I mean, you can do some estimations, but it starts with simple things like calculating distances. Yeah, you can calculate them in Euclidean space, but at some time you realize, yeah, the world is a sphere. Maybe at least I need to know that these coordinates, if I want to do distance calculations, I should probably do spherical distance calculations. Then there is more annoying things like the date-time border. As soon as you're not working in Central Europe, where everything is near and close together, if you calculate distances between New Zealand and California, maybe you want to go over the Pacific and not all the way around the world over the Atlantic to calculate your distances. So it's good if your data store kind of knows that these are not some random numerical values, but that is actually location and geometry behind it. And things get, of course, even more difficult if you're talking about geographical objects that are not just points, but that are lines and polygons. So you actually need dedicated data types if you want to do any data handling on these types of information. So yeah, there is a reason why most database producers now have a spatial extension for their database. It's not just something that they did out of a whim, yeah.
Thank you. Does anybody want to add, or is that all inclusive? Good, and there's a question in the front. Is there one in the back as well? Because then I would take the one in the back that was first, I think, and then the other one.
Yes, my name is Barbara Magania, and it happens that I studied here Geographic Information Systems, and I went to dive into knowledge engineering, and afterwards, now I'm really in the fair data management, and I think it has to do with GIS, because GIS learned me to make metadata more prominent and also to make research more reproducible, because raster GIS already in the 90s, we already talked about how to reproduce a whole series of analysis, and I was very keen on this, and I tried to continue on that. And I wanted to ask you, where are the similarities, or what does GIS or the spatial research with GIS encourages fair data management, and how this relates?
Thank you.
So I think that geographic information or geographic information systems have always put a lot of emphasis on fair-based data management. Of course, at this time, those were different terms. But I also do think that because spatial data often sit at interdisciplinary borders, for instance, the field of geography is one that sits between the social sciences and the natural sciences. so much of the fair part that is about making sure that you can interoperate across data or you can retrieve them using different terms has always been, so to speak, at the forefront or the frontier of what spatial data scientists do. I don't want to toss around names, but if I would talk about all the David Marks on the planet that have done this for many years.
Are we good? Then I would just add another one from the online audience. It's a very broad one. It says, at Linda, you show pretty much maps for the sake of the consumer. I presume that because you have data in a database, you'll be able to ask a question in which you test various combinations of data types and how they relate. So it's a quite broad question that can be answered from a number of ways. Consumer, so it's just the output data is the question, and then this question answering part is in there as well.
So, okay, I'll try and unpack these. So I was showing mapping in terms of the consumer. Yes, mapping can be used throughout. I mean, I think showing as well, just mapping the data as an analyst initially to see where there are gaps in the data is another way of using it. Cartography is a whole sphere of what's right and wrong. And again, I think I would go back to the idea of, you know, do it, but know your limits. And I think probably the most important thing is to be careful how you're reading things. That's actually how we learn as well when we're coming to mapping or graphing, you know, learn to read something. And if you can read a map very well, then you know how to actually create a map very well. What was the other part of the question? Now I've forgotten it already.
In the end, the question was, you have a number of layers in your database.
Yep.
And you want to create information with from that. Mm-hmm. So the question answering part in there, you actually want to ask a question to the 13, 15 billion yep. Semantic connections that Jana mentioned, right?
Mm-hmm. So I think that comes again from understanding the subject as a whole. So whatever your question is that you need to ask of data, that's what you need to hold on to at the start. Think about what question you want to ask, then understand what the data has itself, and then piece those things together. And that's why I think I was saying that there is almost more pressure on the data scientists, the spatial data scientists, to know everything that they can about all of the questions that can be asked of data, because you're not being tasked with the question at first. That's almost the easy thing. If you're given a question, then you go to the 30 layers of data, you find the relevant one, you get your answer. But now you're getting to the point of you have a database of data. Now tell me what's in that data. Give me the answer. But you're never told what the question is. It's up to you as the scientist to find what that question is. And that's actually a very hard thing to do, because you might have something that you want to ask, but that field of information is missing. Or it might be in a different data set and you need to join things together. But for you, it means you actually need to know all of the possibilities and then explore what's in the data and then piece those things together. So you're almost working backwards from where we used to be in terms of knowing the question, going to the database and extracting that piece of information. I hope I answered the question.
That's perhaps part of the spatial data science GeoAI research, no? Because there's a research field of spatial question answering.
Right.
You just formulate an NLP, natural language question that is then translated into an analysis workflow. Good. I'm sorry I need to queue up here, but probably it's a good exercise for the buffet already, for the coffee break in a second. Please let's take the next question from the on-site audience.
Great, thank you. Beth Plaley, RDA US and Indiana University. I have a question for Anita. So Anita, you put out the Taxi New York City example as an example of, you know, efforts to make this data available and to protect privacy were taken. It was a failure. So you suggested that, well, come to me and talk to me about solutions there. And I just would like to probe a little bit on that, because this is a body of people who are trying to use data to facilitate science. So if you could just take that a little bit further in terms of maybe this specific data set or more generally on how these kinds of things are not seen as reasons for people to pull their data in and say, well, I can't make it available because of these kinds of things that will be later discovered. So I guess if you could just take us a little bit further into a path of hope here, I think that would be a good coffee break ending here.
Thanks so much for giving me the opportunity to come back to this topic. Yeah, you're absolutely right. It's a very active field of research, how you can properly anonymize data without losing the reusability of the data, the potential of the data to answer questions. Because the challenge that we are actually confronted with is if you apply a certain anonymization technique, for example, it is popular to only provide aggregated data nowadays. You wouldn't get any more this origin destinations for individual taxis. You would only get information that in district 5 taxis picked up customers, and in another district 7 taxis dropped off customers. You would not necessarily get this one-to-one matching between origins destinations. That's a very popular approach nowadays to avoid these problems. Just aggregate the thing, have a threshold of K-anonymity, or however you want to call it. If there's fewer than 5 data points, you don't give any information about a certain district. This has a lot of consequences, like you might systematically never report anything about certain districts where there are few people around, while you have information about more densely populated areas. So this is maybe not fair to everyone. Other approaches nowadays are like that differential privacy, where you have a certain budget of information that you can't give away without exposing individuals. But also there, to the best of my knowledge, it only works if you already have a set of questions that you allow people to put towards your data set, and it kind of restricts the freedom of what questions you can ask to a certain data set once you have established this budget for differential privacy. So there are no one-size-fits-all solutions to data privacy right now. That's why it's such an active area of research, but definitely people should be encouraged to investigate more and to find out, like, how can we get the most out of the data sets that are being collected around us everywhere without putting people at risk, because that's certainly not worth it.
Thank you, Nita. And that in the end always leads us to a conclusion or open question, actually, how we combine our own ethical and legal standards with operational duties in everyday research. And that's a hard bridge to build. Good. To reduce the waiting times, I would take another question from the audience here.
It's short. I don't want to be between you and your coffee break. So, but it's to Christoph. You know, you don't have to convince me about the value of knowledge graphs, of course. But when we go into the trillions of triples, like we do also in the life sciences, after all, we are not here just to do knowledge representation. We are here for knowledge discovery. And it's extremely hard to discover any new knowledge in a static knowledge graph, as you know. So we need fluid graphs. And whenever any knowledge comes up in one of the millions of nodes that we have, the conceptual distance between that node and all the others changes, as you know. So the scalability of this stuff is very, very challenging at the moment. Do you have any solutions for that in your large graph or not?
How many hours do you have? So
we can take it up in the coffee break.
Yeah, you should take me up on the coffee break. Absolutely agree. So you said a few things that I think we may have an interesting disagreement on. So how well do knowledge graphs scale? That was one question. Well, because they're a rather complex data structure and because you can ask very complex queries against them, they scale mediumly well. On our like 25K machine, we run 15 billion graph statements, and most queries take between 1 second and 30 seconds. So I would say it scales rather well. How much does this scale for very large knowledge graphs? Well, some of you may be aware of Google or Microsoft, and when you use their search engines, you're searching the knowledge graphs. Some of you may talk with Siri. When you talk with Siri, you're kind of using the knowledge graph as well in the background. I would say they scale. I clearly see what you're saying there in contrast to, for instance, some other technologies. So there are a lot of issues left here, absolutely agree. And also spatial or geographic knowledge graphs, for interesting reasons that we can discuss, don't scale so well. The other thing you said was really, really interesting. I think I'm going to take you up on that, about not being able to discover new things. My intuition is that it's the other way around. You have even two ways to do this. You have all your learning, for instance, learning on graphs, for instance, knowledge graph embeddings, and their subtask or downstream task of link prediction. So trying to find a node or the relation between two nodes. But you also have the declarative world, right? So for instance, well, you see now I'm talking for very, very long. I'm just going to give you one example, I apologize. One way to deal with the size of a knowledge graph is that you have to make the rationale or come up with a distinction between how much information you want to have in the graph. So we call this materialized, all the data that is there, and how much do you want to compress your knowledge graphs. So you can have a very small knowledge graph, we call this the A box, and a very strong axiomatization, we call this the terminology. And then on the fly, once you query, you can extract or grow all the implicit knowledge and make it explicit. So you have a very small graph that you grow at query time at the cost of making these queries slow. Thanks.
We'll talk more about it.
I would love to.
And talking about long questions to answers, there is another question from the audience online, which is probably not answerable in one sentence. So, at panel. Unlike geospatial data, other types of spatial data might not have the luxury of well-established atlases. Can you reflect on lessons learned about the importance of having good reference atlas from which experimental observations can have meaningful observations? Talking about reference data and derived information / knowledge from that. Repositories, if that may ring a bell. Catch, perhaps this would be a question to you in terms of how do you deal with ground truthing? Which kinds of information do you need to actually check the performance of your models?
Okay, I mean, when we are working with images, the first thing now is in terms of data, as I said, the problem is not about getting the image. The problem is about getting curated reference samples. So when we say ground truth samples, the first thing, or which is used to be, is like sitting on the computer screen and create hand-curated annotations. For example, if we want to teach the model about buildings, first we need curated building annotations. And then it depends on what kind of application we are going to train. If it is, for example, it's on the semantic segmentation, and then those annotations could be got into binary mask, or it depends on the number of classes. And if someone is going to do on the detection or something, and then they convert that annotation into bounding boxes. And of course, bounding boxes are sometimes debatable, but still they are reference data. And how something is accurate, it's still, yes, we can see buildings are like, we can say, well, this pixel is the end boundary of the edge of the building. So if we say on the how the pixels, how we can sharp enough on the pixels, that's again a debate for the scientific community. And we can take the center of the pixel as a boundary. And that's what we call it reference data.
Thank you. Does anybody want to add, or are we through with that? There is no further question from the on-site audience. Then I would quickly draw a few conclusions, and then we can head off into the mentioned break. So I guess we learned quite a bit here in terms of, let's say, different kinds of notions on what spatial data science is, on what geographic is, on why spatial may be a little bit special, we tend to think, but then again, we're geoinformatics people, so not really representative. First of all, the spatial component to connect different data sets, as Linda mentioned before. In a relational database, if two data sets have no attribute in common, you cannot join them, we would say in technical speak, right? Now, the common ground in this case would be that everything happens somewhere, and then in the end, you can connect via the location. Second thing is representation. There are entire books that are called How to Lie with Maps. And that's exactly what Linda showed. You have a correct representation of this one and the same data set in different variations. And all of those can be questioned, should be questioned. Look at the legend. And that, of course, goes with all different kinds of data scientific outputs, not only maps. Ground truth data. What is ground truth anyway? What's the truth anyway? Oftentimes, we just don't have them. If we do epidemiological analysis, is CDC data ground truth? It is not. It is the official data, but it has their problems, obviously. So that's why I'm saying the confusion matrix is not always the best possible outcome. Yes, you optimize towards a certain data set there, but the question still remains how well you actually represent the outcome, the phenomenon under investigation, and of what quality the results are. And then, of course, the spatio-temporal mop. Yes, the modifiable areal unit problem depends on how large your aggregation reference units are, what shape they have. That is clear. The second question is, if we extend this two-dimensional space that we have in geographic space to 3 dimensions, what happens then? It's multimodal analysis. In short, you have X and Y here, which is meters or degrees, but in the Y-axis, you have seconds or hours. So how do you map 1 meter to how many seconds if you want to go from pixels to voxels, to say? And then finally, of course, data availability. There is this saying, not only saying, a tendency in data science and machine learning over the past 3, 4, 5 years that says we have optimized our models for ages. Now it's more time to actually optimize the data. If you have a very, very good training data set, you do not need a large data set. Because oftentimes there is a saying, the more data, the better. We even saw it before. Sometimes this may not necessarily be true. Good, and there are many geographic applications, of course, including indoor navigation. So I hope you have data to find the coffee break, which is downstairs. Thank you very much for the panelists. Thank you very much for the online questions and the questions here. If you want to follow up, of course, we're all available in the coffee break and throughout the conference. Thank you.